Thank you. So yes, I'm Howard Chu. Very pleased to be here. This is my first time visiting Japan, so I'm very happy to be here at this event. And so this purpose of this talk, we're talking about software optimization, and optimization has, the perspective on it has changed a lot in the software industry over the years. So we'll talk a little bit about where things have started from and where we are today. Some tools that you can use to help you when you're analyzing your own software. Common problems that you might run into in performance issues, and other ways to solve things, and what to do when slow and incremental changes don't get you to where you need to be. And this is all, real-world experience on a living software project. And we have actually accelerated it by a factor of 100 from the first version to the version that we have today. And this is all focused on the C language. Everything that we do is using portable code. There's nothing machine specific. There's no assembly language or any special non-portable tricks. So here I've gone through and found all of the historical versions of the OpenLDAP software, from the very first version on the left column to the version that we've released in the past few months. And you can see, version 1.0, also all of these measurements are taken on the exact same machine. So the only thing that has changed is the version of the OpenLDAP software. So from 1.0, you can see that the first versions barely could do 1,000 queries per second. And the latest version on this same machine is doing, almost 90,000 queries per second. And along the way, obviously there were many little changes we made from version to version, but I'll talk about all of those. So, to write effective code, Donald Knuth wrote this back in 1967. It helps to actually have an understanding of how the machine works. All right, you really have to keep this in mind when you're writing your code. And if you do have that awareness, then it will help you write more effective code. The interesting thing is, a few years later, the same man wrote a cautionary statement about trying to optimize too much. And this particular quote has gotten very famous in the computing science circles, although it's gotten distorted over time. A lot of people have learned this quote as optimization is the root of all evil, or a slightly more accurate, premature optimization is the root of all evil. And you have to understand the full context of the quote, which was that at that point in time, he was seeing a lot of wasted effort trying to optimize code when only 3% of that effort actually paid off. I think that the computing industry took this statement a little too seriously, and in the subsequent decades, they've gone too far away from optimization. So, in particular here, he's talking about 97% of the time you don't need to worry about optimization, and only in 3% of the time is it really going to be important to your code. But the code base that I worked on, where we got a 100 times acceleration, that says that 99% of that code needed to be optimized. So the reality today and the reality in 1974 may not be the same. So how many of you have been working on trying to improve an existing code base? All right, most of you. And how many of you have spent most of your time working on a brand new project, starting it from scratch? All right, just a few. So, the decisions that you make are going to be different based on whether you have existing code that you have to keep working or you're starting a brand new project. But in any case, you always have to plan ahead for how things are going to work out. So, the point about premature optimization, there are some things that you just should know at the very beginning. And so when you think about them, it's never premature. If you need to sort some data in a real life program, you will never use bubble sort. Bubble sort is a good algorithm for teaching in a course, but in real life code, you're never going to use that. And to make that decision at the very beginning of the project is not premature. That's an appropriate decision. And as you're working on things and improving things, eventually you'll reach a limit where every improvement you make is a trade-off where you lose something else, right? But in most of the existing code that you see today, I don't think any of it is anywhere near that limit. You can do lots of improvements without heavy payment. And some things are just obvious. That the straightforward approach is the ideal approach. Right? For example, if you want to add up the numbers in an array, the most straightforward loop, a simple for loop, is going to be the most effective way. You can do more complex algorithms like divide and conquer or logarithmic division, but all you're going to do is make your code more complicated for getting the same result. So there are some times where you have to look and say the most straightforward approach is the best approach. And when you're working on things, to optimize and improve your code, the most important rule is it must be correct. That your code always has to give you the correct answer. If you have a slow program that gives you the right answer, it's fairly easy to make it fast. But if you have a fast program that gives you the wrong answer, it can be impossible to fix it to give you the right answer. So you always start with correct code, and then you can speed it up later. But the other thing too is, you should try very hard to get things right the very first time around, because in a lot of these projects where you're working against deadlines, you will never have time to come back and fix it. So if you can't get things right the first time around, you may never get the chance to get it right. And the last thing to keep in mind is, computers are supposed to be fast. These days we have CPUs that are running 3 or 4 gigahertz clock speeds, and it still takes them 2 minutes to power on. There's the industry, I think, is doing a fairly poor job of writing software. So something to keep in mind is, even if your program produces the correct result, if it gets it too late, I think it's still wrong. So. All right, so whenever you're developing, I think you should always keep in mind the performance goals that you have in mind, and the way to make sure you're approaching them. You have to have some way of measuring your progress. And so the very first thing you must do is profile your code. You cannot tell if your code is doing well or not if you don't measure it. In the modern tool suite, there are many different ways to profile running code these days, right? And each of them has different strengths and weaknesses. The tool that's probably the easiest to use in the Linux tool set is called perf. And you don't have to change anything about your code or the system that you're running on to use this tool. And all it does is it takes statistical samples of the program counter as your system is running. And from these samples, it can show you a map of execution. So again, it's very easy to use and it's very unintrusive, so it has very low impact on the system. One of the problems, though, is because it is sampling, it has a tendency to miss details. It's possible for your program to run through areas of code that the sampler doesn't hit. So sometimes it may not show you everything you need to see. So there's another tool called function check, and this uses the GCC compiler's built-in instrumentation system. It lets you insert special functions at the prologue and epilogue of your main code. So whenever you enter one of your functions, it will call GCC, and you can provide a hook that does whatever you want. And the most obvious thing for it to do is simply to timestamp what's going on. And with this, you get a complete record of the execution time of all of your functions. And so unlike Linux perf, it won't miss anything accidentally. Of course, while it gives you a very accurate result, it slows down your program because it's inserting extra code to make it happen. Also, because it uses a special feature of the compiler, that means you have to do a special build of your code before you can use this tool. And there's another one called valgrind. Now, valgrind is a suite of tools, but one of the subsets in it is called callgrind, and it generates call graphs for you from running code. And this probably produces the most detailed results, but it also runs the slowest because basically valgrind is a machine simulator. So instead of running your code on the native CPU, it interprets every instruction. So it takes 100 times longer to run. So for your first pass, you should probably use perf because it's very easy to use and it has no impact on the machine. On OpenLDAP, we found 55% of our execution time was in the malloc and free routines, and 40% in string routines. So 95% of our execution time was in the C library, and less than 5% of our execution time was actually in LDAP processing. So that's how bad things were when I first started analyzing this code. But you never actually know how bad things are until you look, and so profiling is important to give you some perspective on what's happening. And so just keep in mind that while perf is fast and easy to use, it may not give you the complete picture. So you always have to have multiple tools available to give you a better perspective. All right, have you heard the phrase, don't repeat yourself, DRY? Yeah, so normally this applies to the source code that you're writing, where you don't want to copy and paste things all over the place. You want to centralize as much as possible. I think the same concept applies to the runtime. You don't want your code to repeat itself in computations that it does, all right? So if you've computed some useful data, some useful information, and you're going to use it multiple times, then don't throw it away. Keep it around so you can reuse it. And on the opposite, if you compute something that only gets used very rarely, then there is no reason to keep it cached where it just takes up space. So in OpenLDAP, a large part of our operation is just tearing apart strings and putting them back together again. And 25% of our execution time was just in calculating the length of strings. And this is completely unnecessary because in LDAP, every string that you get over the wire is already accompanied by its length. And so our libraries were discarding useful information that we had to recompute just to perform the work. And so, one of the first things that we did was a complete top-down overhaul of all the string functions. So wherever we were using a bare C string, a char star, we replaced it with a structure that includes the length with the string pointer. And then, the next big offender was string cat, which is used, to concatenate a bunch of strings together, where we tear things apart and then we normalize them, and then we have to reassemble them again. And string cat is probably one of the worst functions written in the C library. Have you seen the joke about Schlemiel the painter? You can get the description at this link. Basically, so Schlemiel is this guy whose job is to paint the lines on a roadway, like down a highway or the dividing lines. And so he's out at his workplace and he's working along, and his boss notices that every day he gets less and less work done. Every day he paints less and less. And so after a couple of days, his boss asks him, Schlemiel, why is it that every day you paint less and less and less? And he says, well, every day I have to walk back further to get to the paint bucket. So he's always starting from the same place and adding to the end, and it gets longer and further away. And that's the same thing that's happening in string cat. It's always starting at the beginning of a string and adding to the end of it. And so the more you use it, the slower it gets. And so in our code base, we replaced all the uses of string cat with a custom function of our own that simply returns a pointer to the end of the string instead of returning a pointer to the beginning. And so if you have the end of the string, you can just concatenate to that immediately without any extra wasted time. And the funny thing is that the modern C libraries now actually have a function that does this, and it's called STP copy. All right, so this is a little bit of a side note. One of the big problems in C is that it's very easy to hit buffer overflows if you've miscalculated how your string buffers are allocated. This is a very safe function that we have started using that will never buffer overflow, because you always pass in a pointer to the end of the buffer and it will never write past it. The other thing is, like the previous function, STP copy, it will return a pointer to the end of the string. So it allows you to do fast concatenations as well. So unlike functions like strlcat or strncopy, whatever that other modern C libraries use, they all have the problem where you always have to recalculate the remaining length of the buffer to use them safely. And the calculation is where all the bugs creep in. So this avoids all of that. And it's a fairly simple thing, to use a function like this. So when you have, major problems that have very easy solutions, you should definitely apply the easy solutions everywhere you can. All right, so if your code is doing a lot of string handling, you probably don't want to use just the normal C library string functions, and you don't want to use plain C strings. You probably want to use a structure that includes the length everywhere. Okay. So the next big problem area, the biggest actually, was in memory management, Malloc and free. And these days, there are very good high-performance Malloc libraries like JE-Malloc or Google's TC-Malloc. But if you see that you're spending a lot of execution time in Malloc, your first response should not be to just replace the Malloc library, because you won't get very big gains out of that. 10%, 20%. So, if you really want to attack this problem, you have to understand how you're using memory and see where there are ways that you can avoid it. Most of the functions that were in our code base looked a lot like this, where you want to operate on some data and then return a result, and the function always malloced a structure to contain the result. Okay, this is a very common pattern in a lot of code written in the 1990s, I suppose. And you can completely eliminate that use of malloc if you just, pass in the structure pointer in the parameter list, because very frequently the parameter only gets used in one level of function. So you don't need this long-lived Malloc variable because you're only using it in one place and you're going to throw it away right away. So as soon as we changed our memory usage pattern in this format, we got a massive gain, 4x performance gain just from that. So, the lesson here is don't do things the way C++ does. This is a very common pattern in C++, and it's just a stupid one, right? Just don't do it. Okay, so this is a very obvious pattern. As soon as you see it in your code, it'll jump out at you. But after we fixed this, then that was like the last really easy and obvious thing. We had to start looking more carefully after this. Okay. So another one that hits is, if you're building a long result value and you build it incrementally, the C library gives you this realloc function that lets you grow the size of a buffer. You should never use this. It's the same problem with stringcat, where it always starts at the beginning of your buffer and copies the contents over. So the more you use it, it gets slower. The easy solution here is whenever you have multiple items to put into a list or something, count them up first, count up the entire size that you're going to need, and then allocate it just once. Okay. So in an LDAP server, we receive LDAP messages over the network. We have to parse them, store all the fields into a structure that the rest of the server can operate on, and all of this again was heavily using Malloc to allocate space for each individual field, and then copying all the data into the fields. So again, this is a lot of excess allocation and copying that we didn't need to do because the data is still sitting there in our original read buffer. All we had to do was point into that buffer. And so making this change made our library processing 0 copy, so everything was much faster from that. Okay. So, again, in OpenLDAP, we process one LDAP request at a time over a socket. So whenever you have, easily divided work units, where all of your processing happens on one request or one task, whatever that happens to be, there's a good potential for you to use something like an arena-based memory allocator instead of the library heap. In this case, you provide one arena per request, do all your allocations in there, and when the request is done, you just reset the arena to 0, and you don't have to spend any time doing any freeze. Funny enough, this is the memory management approach that was used in Pascal in the 1980s, and it's somehow it got discarded, but it's very simple and it's very effective. It's very powerful. So another thing is, if, again, like in slapd, we allocated a structure for every incoming request. Now, if you're going to do this frequently, we're doing this millions of times per second now, it helps to pre-allocate a number of them so that you always have them available. And that just avoids the overhead of using the Malloc functions. So using the set of techniques I just outlined, we've almost completely eliminated use of Malloc. It doesn't even show up in the top 100 functions of our call graph anymore. Now, while you're looking at the memory that you allocate in free, sometimes you'll make some mistakes and you'll see that you have a memory leak in your program. This little tool that I wrote is very useful in that case. It'll help you track down the memory leaks, and it's very fast. It's at least 8 times faster than the memory leak tracer that's in glibc, and it's hundreds of times faster than the one in Valgrind. So it'll save you a lot of time. All right, so after you've done the obvious things, the string handling and the memory handling in OpenLDAP, that got us at least 60 times faster. After you get to that point, you may find that there are no obvious peaks in your call graph anymore. Now, if your system performance meets the goals that you want, then that's great. Your work is done. Everything is working well. If you actually need to get further, then you need to do some more deep analysis. And a lot of the things that are coming up next, they won't actually stand out in a profile trace. So the very the very first release of OpenLDAP 2.0, we switched to a thread pool, because in 1.0, we were allocating a new thread, spawning a new thread for every incoming request. And as each request ended, we would kill the threads. And it turns out that starting threads and killing threads actually has a fairly substantial cost, even though it was supposed to be very cheap and lightweight. So again, this comes back to the don't repeat yourself principle. If you're going to be starting and stopping things over and over again, that's wasted execution time. So instead, you use a thread pool, you start some number of threads once, and you keep reusing those threads over and over again, and that avoids that overhead. And this gave us a 15% improvement just by itself. One of the interesting things that, again, we didn't think about at the outset, we have debug functions scattered throughout the code. And you turn on various log messages so that you can see what's going on. But when you don't have those logs enabled, you want that debug function to do nothing. And it turns out that just to invoke this function that checks a value and decides to return without taking action has a significant runtime cost. So instead, we started wrapping these invocations with a macro that puts the condition test in the macro instead of invoking the function. And again, a simple change like that, is worth 5% of runtime. The other interesting thing we had is functions with very long signatures. The LDAP search request actually has 14 parameters, if you look at the message on the wire. And so in the library and in the daemon, we have to pass 14 parameters up and down the call stack. And if we're going 5 or 10 levels deep in the call stack, that's a significant overhead. And as this guy Alan Perlis wrote, if you've got a function with like 10 parameters, you've probably missed one. And once you've gotten to that number, you've probably overlooked something. So you've probably done something wrong. So every time you get to that, that's a really big red flag. I noticed this a lot in C++ code bases, and well, I hate C++, but in C code bases, it's fairly easy to avoid this, and you should stay aware of that. So again, instead of having these 14 parameters being passed around all the time, we started putting all of them in a single structure. And so to pass these up and down, we only need to pass one pointer to a structure. And that saved 7 or 8% of our runtime. Okay. When we first started writing multi-threaded code, we only had single processor machines to develop on. And that was 1988, 1999. It turns out when we started moving on to dual core or multi-core machines, that we were seeing new overheads that we'd never noticed before. And part of that was because we had data structures that were being accessed from multiple CPUs poorly, right? Let's say you have two variables adjacent in memory, and they're being accessed independently by two different CPUs. But if they happen to be aligned, with bad luck, so that they both reside in the same CPU cache line, then every time one CPU modifies one, it will invalidate on the other one, right? And so this hit us pretty intensively when we started doing multiprocessor machines. A typical CPU cache line is 64 bytes. So if you have a bunch of integer variables that are only 4 bytes each, and you have them being accessed from multiple threads at the same time, you have a high probability that some false sharing is happening here. So the approach you should take here is when you define your structures, you should pay attention to the ordering of the fields in the structure. It's ideal is if you put if you order them from the largest to the smallest, and the goal is to avoid extra padding bytes in between unless you actually need them. So there's a conflicting goal here, because you want to avoid padding bytes as much as possible, but for cache alignment purposes, you do put padding in where it will save you and where it will allow things to line up to, say, a 64-byte boundary or whatever it happens to be. And if you don't manually align your data, typically the C library will give you memory that's been aligned to 16-byte boundaries. And so if you want to align to a cache line, you might have to readjust the memory size yourself. Or you can use something like POSIX Memeline, which does that for you. Now, the overheads that you're paying here, again, they won't show up in a standard profile, but on each CPU, they have their own performance counters, and the Linux perf tool lets you access those counters. So you can see the overheads and the effects of your restructuring if you use perf. And then one last thing that we didn't, again, is always hidden. The funny thing about an instruction profile, a runtime profile, is it shows you where CPU time was spent executing your code, right? But if your code is stuck waiting in a mutex, the CPU isn't actually executing anything there. So the time that you spend in a mutex, even though it may be significant, it doesn't show up in a standard call trace, in a standard profile. In OpenLDAP, in slapd, we had a single work queue that manages our thread pool. And when we started running this on a 4-processor machine, we found there was a very major bottleneck there. And if we just replaced that single work queue with 4 work queues, one for each CPU, we found that the contention there, the overhead, actually decreased by a factor of 6. The relationship there is nonlinear. You get a much bigger payoff than the actual change in size. All right, so one of the things you realize here is all of this work is iterative. Every time you solve one bottleneck, it will probably reveal another one, that was hidden from the first time. So sometimes it will look like it's an unending task. I've been working on OpenLDAP since 1998. This is over 20 years working on this code base. It may feel like you're just on an endless treadmill. It's important that you take good notes and take good notes of your measurements, record your measurements, so that you can see the progress you're making. You can relate the changes to the code changes that you've made. You always have to be able to backtrack and see, what changes did you make to get to the state that you're in. So yeah, keep good notes. And then sometimes, after all of this iteration and refinement, you'll discover that the changes you've made just aren't good enough, and no amount of tweaks will get you to the results that you want. And in that case, if you actually have a well-defined list of the remaining problems, if you know exactly what there is left that you need to solve, it's possible that the best solution is to start over. Generally, this is something you want to avoid as much as possible, because starting over can mean you actually wind up recreating all the same problems the second time around. So you do have to have a clear view in mind of the problems that remain that must be solved. So in OpenLDAP, we've been using Berkeley database for a long, long time. I've at least 15 years now, and we've spent endless hours on the code to make it perform very well, because on its own, Berkeley DB is very slow. And it was too slow to use just as a native backend. And so we had, in our own benchmarking and testing, we said, okay, well, we can speed this up by putting a cache in front of it. And that seems to be always be the solution. If you've got a slow web server, we'll put a cache in front of that. We'll put memcached, or we'll put some other squid or some other proxy cache in front of it, and that's not always the right answer. The cache layer itself was so complex that it started to introduce new bugs just on its own. And so the real thing for our situation was to realize when the database is so slow that you need to put all these band-aids around on top of it to make it work, that it's probably not the right database to be using. So for example, in Berkeley DB, it maintained its own data cache for all the records it was managing. And we had to put our own data cache on top of it to run fast enough. And all of the data that you read and write from your data files is also being cached by the operating system. So it lives in the file system cache too. So a lot of the time, the data that we are manipulating is in 3 different copies in memory. It's in the file system cache, it's in the Berkeley DB cache, and it's in the OpenLDAP cache. So that's terribly wasteful. And as our database sizes got larger, it just became much harder and harder to manage and to tune. And then the other problems that we encountered was the Berkeley DB has its transaction management system, which has a very complex lock manager built into it. And even when you operate this thing perfectly correctly, all of the time, the lock system runs into deadlocks. If you're doing modifications from multiple threads concurrently, it will deadlock against itself. And this was a normal thing in the Berkeley database. It was an expected result. And so if you ever got an error code that says deadlock error, you have to abort the transaction you're operating on and back off for some random amount of time and try again. So as your system load goes up and more threads start to get busy, the busier you got, the slower the database got, because it would deadlock more often and you would start needing to back off more often. So that's just in the database layer itself when it was working properly. And then we had to put our own lock manager on top to maintain our cache. And so everything just got far too complex and far too slow. So in 2009, we started looking at designing our own database layer, and specifically because of these caching and locking problems in Berkeley. Now, changing the entire underlying data store in a large software package is not the easiest thing to do. In our case, it was okay because we had a modular backend interface already. The Berkeley database backend that we were using was actually the second major backend that we'd written with this modular API. Rewriting the entire thing from scratch is usually a bad idea. It can cause more problems than it solves. But if you keep track of the actual goals that you need to fix, it can play out well for you. In the case of LMDB, we use multi-version concurrency control, which lets us do reads with no locks at all. So that was an immediate performance win. Search operations are much faster because they take no locks. And because we are using a read-only memory map where we return a pointer to the data, we don't actually need to do any Alex or copies to return data to the caller. So that was another huge performance win. And again, because we're using a read-only memory map, we never overwrite live data. The database is completely crash-proof. It will never corrupt in a system crash or anything. Okay, so the things to keep in mind, your code must be correct first. Before you do anything else performance-oriented, it must be correct. The approaches that you get to get better performance are going to be iterative. You don't expect to get perfect gain in one step. There's a lot of tools available to help you on your way. You're probably going to need to use more than one of them. And sometimes, you have to throw out a lot of work and start over to get the results that you need. And the main point of all of this, is you want efficiency. You want to do only exactly as much as you need to do and nothing more. So do what you need. Do what you need once if you can, and don't repeat yourself. So.
Thank you very much. Next, この後、質問の時間とさせていただきます。こちらの質問の時間、通訳の翻訳が入りますので、日本語でも、質問することができます。質問されたい方、どうぞ手を挙げてください。では、前の方の真ん中の列の3列目にお願いします。
ありがとうございました。C++ が嫌いというふうにおっしゃっていたんですが、僕は普段 C++ を書いているんですが、どうしたらいいでしょうか。
Could you repeat the question part of that?
C++ で、同様なことをするにはどういったことに気をつけるべきでしょうか。
Okay, you should be aware of the complexity of the classes that you design. When you put methods on classes, you should try again to minimize the size of your parameter lists. You really should. In my opinion, you should avoid using constructors and destructors too frequently. Yeah.
Thank you.
ありがとうございます。次にご質問ある方いらっしゃいますか。では、真ん中の列の通路のところの黒いシャツの方、よろしくお願いします。
ありがとうございました。先ほどスレッドプールなどでDRY Not Repeat Yourself ということでリソースを再利用していくことでより効率的になるというお話をされていたと思うんですけど、よくそういった時に問題となるのが リソースの状態が複数のパターンで共有されることでデバッグが難しくなるっていう問題があると思うんですけど、そういう問題に対してどのように対処しているのか教えていただけますでしょうか。
Well, I suppose defining the boundaries of your modules is always, an important part of the design process. There's, one of the goals there is always to keep your data close to the things that process it, right? So when you're looking at data that gets shared, you should think about how much of it really needs to be shared. And then when you're looking at, for example, a thread pool, which is going to be reused amongst many different modules, you try and keep the interface as simple as possible, and you want to have a single entry point, and you can do your locking or concurrency control on that single point. That's it.
ありがとうございます。
ありがとうございます。次にご質問のある方、ではちょうど目の前のお願いします。
最初に2つのホットスポットを、取り除いて、その後に、速度が十分であれば通常はそれで終わりであるというふうにおっしゃっていて、私であればそこで仕事を終えると思うんですけれども、そのオープン LDAP にとっての十分な性能というのは一体いつ達成されるのかというか、そういうものが来る日はあるのでしょうか。
On the performance side, we are pretty much there. At this point now, we can answer a query in under 0.5 milliseconds, right? And like on that graph where I showed you, the server was running those queries in about 0.6 milliseconds, and the ping time on that network was only 0.4 milliseconds. So we're basically answering queries at just slightly over the delay time of the network itself. And that's really our goal, is where we wanted OpenLDAP to run at the full speed of the network. That's put us in a position to, since 2005, OpenLDAP has been the world's fastest directory server. We now have telephone companies all across Asia using it, and it's the only software that they can use. When they have hundreds of millions or billions of accounts that they're managing, and you need response times of on the order of milliseconds or microseconds even. OpenLDAP is the one that does that. So yeah, on the performance side, we're pretty much there. There are still some performance improvements in the OpenLDAP 2.5 release, okay, but mostly those are to handle larger scale. For example, in 2015, we did a benchmark on a 64-core server, and we were reaching 1 million queries per second, which was good enough for then. In 2017, we did a benchmark on an Oracle Spark machine with 2,048 cores. Okay, and in that case, we found a couple of bottlenecks that we needed to remove, and which we did. So, from the performance angle, on a certain scale of machine, we're already there. On a larger scale of machine, we had a few more things to tune.
ありがとうございます。
ありがとうございます。他にご質問ある方、どうぞ手を挙げてください。左側の上の方でお願いします。
バークレー DB から、LSDB に 実装を変えたとのことなんですけれども、他に組み込みの、DB を利用しなかった理由ってあるんですか？例えばレベル DB とかビットキャスクとか。
Yeah, we looked very hard at all of the available embedded databases, but around 2008 or 2009, there weren't a lot of other good choices. We'd used, obviously there were the GNU database and some other similar products, but besides Berkeley, none of them supported transactions. And that was a key element for us. Yeah.
Okay, you need transaction, that's right? Transaction.
Yes. Yeah.
Okay, thank you.
ありがとうございます。他にもご質問ある方、どうぞ手を挙げてください。では真ん中の中央の下の方のお願いします。
ありがとうございます。今回の話が、一つのマシンの中で動かすプログラムの最適化が中心だったかなと思うんですけれども、その複数のサーバーがクラスター構成をとって、連携しながら一つの機能を実現するみたいなサービスの時に、全体としてのパフォーマンスを最適化するみたいなところに対してはちょっとどういうふうなアプローチを取ればいいでしょうかというの、何かアイデアがあればお伺いしたいです。
Yeah, that's a more challenging situation because generally when you are coordinating a cluster, that means you have something in the front that distributes work to the cluster nodes in the back, and you will find that this central point becomes your main bottleneck, right? And in that case, the best thing that you can do is to try and completely minimize the amount of processing work that this load balancer, this load director performs, right? So you want it to do as little inspection of the data as possible. You want it to do as little copying as possible and act as much like a transparent pipe as you can. To do as little processing, real complex processing there as you can. This is a problem that we've actually been working on ourselves. There's a new feature coming in the next Open LDAP release where we've provided our own load balancer. And the reason we've done this is because other third-party load balancers don't perform well enough. And this is something we've addressed specifically. Yeah.
ありがとうございます。
ありがとうございます。まだ他にご質問ある方いらっしゃいますか？質問ある方どうぞ手を挙げていただけたら。では一番前の列の方お願いします。
お話ありがとうございます。僕 LMDB を仕事で使って非常に満足しています。でちょっと聞きたいんですけども、 LMDB ってすごいパフォーマンスいいしトランザクションあって便利なんですけども、あれを作るにあたって何かブレイクスルーがあったのか、それとも地道なエンジニアリングなのか、どちらなのかを教えてください。
Well, we started thinking about it in 2009, and the first release was 2011. So there was a lot of thinking and design that happened before we actually, got working code. But once, and also when we were designing it, we weren't actually sure that it would perform well. It was completely unknown until we got it running. And so yeah, once we got it running, it was far better than we expected. Yeah.
ありがとうございます。Thank you.
ありがとうございます。他にご質問ある方いらっしゃいますか？若干質問の時間しっかり取れております。ご質問ある方どうぞ手を挙げてください。では質問の方終わったみたいですので、すいません、お願いします。
LMDB に関連するんですけれども、よくこのコンピューティングの世界だと、例えば論文とかで新しいデータ構造とアルゴリズムが提案されて、でそれに基づいて新しいファイルシステムとかが突然ポーンと登場するってことがしばしば起きているように思います。そういった論文ベースで何かこういう新しいデータ構造とかアルゴリズムが登場したぞっていったのを追っかけているっていうような活動をやっていって、その上で LMDB とかそういった新しい方式を導入するっていうようなことがされているんでしょうか。個人としてだけじゃなくてプロジェクトの中でそういったことってしばしば見聞きとか実際にされたりしていらっしゃいますか
？Yes, I review data structure research all the time. Now the funny thing is, LMDB is based on B+ trees, which have been around since the 1960s or 1970s. There's not a lot of new ideas in that underlying structure. But the funny thing, the B+ trees work extremely well, and they are extremely well suited to systems with multiple layers of memory hierarchy. They work for fast local cache and slower secondary storage. And a modern computer is all about, fast on-chip caches, slower level 3 or level 4 caches, slower RAM, and then slower disk. And so the basic design of a B+ tree hasn't yet been outperformed by these, the newer things that I've seen.
ありがとうございます。
ありがとうございます。他にご質問ある方いらっしゃいますか？多分最後の1個のぐらいの時間になっております。ありましたらどうぞ手を挙げてください。ありませんかね？真ん中の通路のところの列。はい。
素晴らしい講演ありがとうございました。LMDB を開発されようとしたときに、新しくいろんな人材を集めなければならなかったと思うんですね。特にデータベース技術者というのは非常に高度なコンピューターサイエンスの知識が必要だと私は認識しています。そういう仲間はどうやって集めてきましたかっていうのが質問です。
There was no new resource. That was, my design work.
恐れ入りました。Thank you so much for your response.